Just deciding to be buggy only all the days. I'm really sorry about this. Yeah, the response rate is really bad. No, what is happening? Right. So we are going to talk about economic load dispatch, right? So basically, the first concept that we will come across is that of a load curve. A load curve. So basically, load curve is nothing but kilowatts versus time, right? So it can be for a long period, short period. Guys, I'm just pausing this for a minute. I'll be back. Okay. Thanks a lot. Right. So let's refresh. Start. So we are talking about economic load dispatch, right? So this is something that they have added to the syllabus, and the first thing that we're talking about is something called as a load curve, right? So load curve is nothing but kilowatt hours, kilowatt versus time, right? This is the load. So it can vary if you look at the load curve for the, basically if you look at the an average load curve of the, for a country like India, this is for say day, right, for 24 hours, right? So this is 0, this is again 24. So you will see that the load will be somewhat constant at this time. Then in the morning it will go down, then it will come up, and then it will peak during the evening time because of the lighting load, and then again it will come back to the normal. This is kind of the average Indian load curve. And with respect to India, the good thing is that we have so much demand, and the um, supply is yet to meet. We almost have a very the average curve is very steady or straight, right? Okay. So from the load characteristics, we can always find the, what will be this? This will be the maximum demand, right? This will be the minimum demand. We can also find the average demand. How do you find the average demand? You find the area of this curve, and then you divide it by the number of hours or days. So that will give you the average daily load, right? Right. So based on these, there are few terms that we need to look at. The first one, load factor. Right. What is a load factor? Load factor is basically average load divided by maximum load. Right. Then based on the time frame, right? Based on the time frame, we have different types of. So then there is daily load factor, right? Which is number of kWh generated in a day divided by 24. Basically, the total energy that is generated in a day divided by 24 is the daily load factor. And monthly will be basically number of units generated in month divided by 24 into the number of days. And then yearly would be number of units generated in a year divided by 24 into number of hours in a year. I think it is 8,000. This many hours, right? It is 24 into 365. Right? I don't know. 1 0 less 1 0 more. It should be more or less. This is basically 24 into 365 would be your yearly load factor. Right? The next thing that we need to find is demand factor. You on the slide? Okay, 8760. Fine. Thank you. Please create another. Right. So then we have demand factor. What is demand factor? So make sure you note these things and put it in a formula book of sort. Right. It is basically maximum demand by connected load. So these are different. And tell me how they're different. See, suppose you are in your house, right? So in your house you have say 10 plug points, right? Or more 10 electrical outlets. Like you have three bulbs. So you are living in one room. So you have three bulbs, one fan, right? Two electrical output, right? Maybe one AC, right? It's the sockets, right? AC. So what is connected load? It is the total sum of all these devices power rating. So three bulb is 60 into, say suppose you are using three incandescent bulbs. So that would be 180 watt, right? And you have fan that probably is 100 watt, right? And two electrical outputs. You can connect many devices. So let's go for the maximum rating, which is 1000 watts, right? And one AC. It depends on what kind of rating you have. Let's put it at 1000 watts. Nothing. I'm going for the maximum over here. So you probably have something like 2280. So this is the connected load. But in a given day, you probably will not operate all of these together. You probably operate one LED, sorry, one bulb, one fan. Maybe you won't operate fan and AC together. You maybe won't connect. So the maximum demand probably will be somewhere in 1100. So the demand factor is how much of the total connected load do you get as your maximum factor. Is that clear? Right. Next thing that we need to look at is the capacity factor. So this is for a generating unit. So this is actual energy produced. So energy produced, right? Max energy that can be produced. So given you see, suppose you have 3 generators in the generating station, so there will be a maximum energy that you can produce. So actual energy be maximum energy, right? And there is something else. These are trivial. This is called as an operation factor, right? Which is basically number of hours of operation. Number of hours of operation divided by total number of hours in a year. Right? Right. Okay. So these are few things. And let me see if there are some other factors. Okay, let's look at a question based on this. Did we discuss load factor? No, we discussed load factor. Uh, what is the problem? This one. This is basically total number of hours in a year. Okay, so let's do one question over here. So generating station. Okay, so let's try this question. Do you guys, can you attempt it? Or do you need help? Okay, so just look at the formulas that we discussed earlier. You should be able to solve this. Okay, demand factor is 0.465, correct. What about load factor? We discussed load factor. Yeah, so that is correct answer. 0.465 is correct. What about are you guys doing this? Okay. What is it? 215, is it that factor or percentage? It has to be wrong. So what is load factor? Load factor is basically average demand divided by maximum demand. So we know that what is maximum demand? So we know the denominator. So the denominator is 20 megawatt. But we don't know what is the average demand. Right? So you got the answer. But we are given the total units that are generated. So total units generated is 61.5 into 10 power 6 units or 6.5 kilowatt hour, right? Divided by number of hours in a year, is 8760. So if you do that, you will get average demand as 7260 or 7020 kilowatt. This is average demand. So this is 7020 kilowatt. So if you divide, you will get it as 0.1. Is that clear? Okay, let's do one more question. Can you guys give it a try? Is this something that you can see? It's just straightforward. Mm, what's happening? One zero one 10.5. Varun, did you get your answer? Correct. Yeah, it's 1051 2 megahertz. Right. Thank you. Okay. See if we have one more question. No. Then let's get into the economic load dispatch. Right. So these were the factors that we looked into. Now let's go into economic load dispatch. So there are two concepts that basically you need to understand when we go into economic load dispatch. What is economic load dispatch? Right. Uh, Suppose you have n generators in the system, right? And they will have, so the total generating capacity would be what? Sigma I is equal to 1 to n pi, right? Each generator will have its own maximum generation capacity, so this will be our total generation capacity. So at any given point of time, our load will be, preferably in an ideal condition, it should be less than or equal to this, right? Total load will be less than or equal to this. The total load is equal, then there is no confusion. You generate all operators in the maximum critical capacity. But if it is not, then we have to decide how much each generator has to generate. Let's say suppose You have generator 1, generator 2, right? So both are serving a load. So suppose we need 100 megawatt and both generators are rated 1000 megawatt, right? Then there is infinite number of combinations on how we can do, right? We can say generator 1 generates 100 megawatt, this generator generates 0 megawatt. The next combination is this generates 0, this generates 100. We can say 50-50. We can say 30-70. So it is possible that we can find different combinations. So which combination do we take? So that question is answered by economic load dispatch, right? Hmm. So what is the criteria over here? So this is basically deciding this one, how much each generator is generating is called as, that problem will be called as load dispatch. And economic load dispatch will be when we consider the cost of power generation. So the objective is meet PL is equal to PG with minimum cost. That is economic load dispatch. There is also one more routine or one more process that we involve, but we are not looking at it right now. It's not part of the syllabus, but it's good to be aware of it, which is called as unit commitment. Unit commitment is basically that all generators are not always connected to the system or will not be generating. So what we decide is, suppose we have n generators, we'll say n generators should be on and n minus n generators will be off. So deciding which all generators needs to be turned on to supply the load is basically called as unit commitment. And based on, so suppose then we will decide out of n generators, m generators will be on. And out of this m generators, how much each generator will supply is decided by economic load dispatch. So this is a two-step problem. Basically, unit commitment decides which all generators will supply the load. So unit commitment answers the question which right. So unit commitment answers the question which, and economic dispatch answers the question how much. Is that clear? Clear. Are you guys here? Right. So why do we have this problem of economic load dispatch? The reason is different generators have different cost, right? This is the reason why we have this problem. If all generating units had same cost, then it doesn't matter who generates how much, right? So different cost per unit for different are different. So the assumption that we are going to make over here right now is that all units are thermal units. Right. So what are we trying to optimize over here? We are trying to optimize the cost. And what is the major cost when it comes to thermal power plant? It is the fuel cost. So cost of ith unit for generation of PI is basically, so this is urgent relation, A half AI, A square, there is a quadratic component, then there is a linear component, and then there is a fixed component. So these two components are variable. It will change with respect to the amount of power being generated, and this is a fixed component. So if we are looking at something like a nuclear power plant, this formula holds. But if you're looking for something like hydroelectric power plant, this will be the major component and this will be the smaller component, right? Right. Then there is something called as a fuel cost curve. Hoping you guys, this notification is not. Can you guys send me a message on this thing? Because I'm supposed to get pop-up alerts, but I'm not. Okay. So the next one is called as a fuel cost curve, which is an important factor. Right? So this is our cost, which is how much rupees per hour, and this is our PL. Right? So basically, for generating, this is our PA minimum. This is our PA maximum. Since we are having a quadratic relationship, it will not be linear, and this is one of the important things. PA, this, if you remember, this was one of the conditions that we looked. P max, P min. This is called as a fuel cost curve, right? So why do we have P min? Why is it not going all the way to zero, right? An ideal condition should be between 0 and PA max, right? It is not so because boilers are required to maintain a minimum temperature, otherwise it will lead to boil instability. So even with respect to hydro power plant, even with respect to nuclear power plant also, we will have this issue that there will be a minimum power generation that we need to maintain for the system to physically operate correctly, right? And what is PA max? PA max is basically generator's maximum rating, right? It would be PA max is usually S max, which is 23 EL. Okay. So let's look at an example. So we have two generators. We have our P output or P load, right? So this is our G1, this is our G2. So the cost of this one is rupees 5 per megawatt hour. So this is a cheaper generator. And this is rupees 10 per megawatt hour. Okay. Then this generator, the maximum generation capacity is maximum is 70, right? Here the maximum is 100, right? So basically, the first question we are going to look is unit commitment. So if PD or P load is 50 megawatt, what is ideal status for 1 and 2? So consider this is switch number 1 and this number is switch number 2. So if we are only supplying 50 megawatt over here, what should be the condition for 1 and 2? On, off, on, off. So should one be on, off? So what is the combination? Is it on, off, off, on, off, on? So the first one is for switch number 1, the second one is for switch number 2. Off does not make sense because we need to supply the load. Look at the parameters given. This is very much intuitive. It's basic decision making because it's not even power system, right? Okay, you're saying generator 2 should be on and generator 1 should be off, is it? Okay, Varun? On off. Okay. So look at it. We have to supply 50 megawatts, right? We have to supply 50 megawatts. Let's supply 50 megawatts. So this generator can supply up to 70. This generator cannot supply up to 100, right? So if say suppose if we turn on generator 1, what will be the cost? It will be 50 into 5, right? 50 into 5 into 10. That is basically 250 T, the number of hours, right? If instead if we go for this and this, it would be how much? It would be 500 T. If you see, this is less. So we always want the cost to be less. So basically, it is generator 1 has to be on and generator 2 has to be off. Is that clear? Is that clear? Okay. Right. So then let's look at something called as reserve, right? So this is a concept that is very strong in day-to-day operation of power system. What does reserve mean? Reserve is basically, see, suppose current demand is PL, but we will schedule generators for PL plus X, so that if because we don't know how the load varies, right? We can't exactly say how the load varies. So suppose we exactly schedule for PL, right? And if the load varies, then we'll have trouble. So we will keep some capacity extra. We'll keep the generator capacity extra so that if there is any difference, we can pick it up. Say suppose in the earlier case we had connected generator 1, right? So what is the maximum capacity of generator 1? It is 70 megawatt. How much were we generating? How much were we generating? We were generating 50 megawatt. So the difference, right? The difference. So total 70 megawatt capacity is connected to the grid. So reserve is basically 50 minus, sorry, 70 minus 50, which is 20. So basically what we're saying, we can handle up to 20 watt increase in the grid. So there are three types of reserves. The first one is called a spinning reserve. Right? Spinning reserve is if the generator is already connected to the grid and is already supplying power. Like this is a spinning reserve, right? Then there is hot reserve. So hot reserve is when the generator is connected to the grid, but it is not supplying any power. No, it's not connected to the grid, but the boiler is hot, and if you connect it, it can immediately start supplying. Right? That the turbine and everything is operational, but they are not supplying power yet. Right? That is hot reserve. And cold reserve is basically we have to bring it up. So this can take it up immediately. This also will take it up immediately, but there is a switching action required. This will take some time. Right? Right. Clear? Okay. So as I was saying, the main objective of economic load dispatch is to minimize. So basically, this is an optimization problem. Total fuel cost. Total fuel cost or total cost, right? And so if you are familiar with optimization, basically this is called as an objective function, and then there will be some constraints. So the idea is we need to minimize this based on few conditions. So what is the first condition? Okay, right. So this is the objective function, and what will be our so first one will be the load should meet the, so the demand should meet the supply, or supply should meet the demand, right? So Pi in the practical condition, this also will have to meet the losses. P losses plus P demand should be the generation supply, right? Then also there will be something called as reserve constraints, that UI Pi max for each generation there should be, that this should be greater than or equal to PD plus Pmax based on the reserve condition. What is UI? UI is the unit commitment decision. So it can be 1 and 0, right? If a generator is on, this will be 1. If it is off, it will be 0. So what happens? This will go away from the system or set of equations, right? Then on top of that, there are a lot of other, actually a lot of practical conditions that we probably won't cover over here based on because of the limitation of the syllabus. But there are more conditions like minimum generator on time, so there is a minimum time that the generator needs to be on. There is minimum off time, right? Then we need to consider the transmission constraints. So the transmission line will have its own power limitations. So suppose you, in this previous question, here we are assuming that this line can handle 70 megawatts. Sometimes what happens, this line can only handle 30 megawatt. So we have to limit the generation over here to 30 megawatt because the transmission line can only handle that much. So we have to consider the transmission line constraints and many other factors, right? Are you guys with me so far? Good. Right. So let's look at something. So here we said that this is our factor, right? So we need to find something called as to formulate the economic load dispatch. We need to need a term called as incremental fuel cost, or this is an important term. So this is a always these kind of terms are extremely important when it comes to economic load dispatch. Right? This is a very important term. So IC of generator I is basically cost of generating power divided by P. So it is basically the incremental cost. When you are increasing the generation by 1 unit or 1 megawatt, how much will the total cost increase? It's like a marginal cost thing. So the unit is still rupees per megawatt hour, right? So we know that what is cost. It is AI pi square plus bi pi plus small ci, right? So if you differentiate it, what will you get? It is ai pi plus pi, right? So basically, incremental cost curve, if you plot it, you will find that it is a linear thing. Right? It's a straight line, right? Where the y-intercept is bi and the slope is ai. This would be our pi min. This would be our pi max. So this is our incremental cost curve, right? So first let's look at economic load dispatch without losses, right? So this is without power losses, ED without losses. So what would be our optimal condition? Objective function would be minimize total cost CT, that is sigma I is equal to 1 to n, where n is the total number of generators in operation, right? Pi of Pi, where Pi is the individual generation. And what are the subject to first one? What is, since we are not considering losses, right? What will be our first condition or first criteria? Is the load balance equation, right? That is sigma Pi is equal to P load. Usually there should have been with P loss, but since we are considering without loss, it is sigma Pi is equal to sigma. So if you rearrange, it would be PD minus sigma Pi is equal to 0, right? Now this is the equality constraint we have. Then what is the obvious inequality condition we have? Each generator will have its own maximum and minimum, right? Pi min less than or equal to Pi less than or equal to PI max. So we can't say that PI should be less than this one. So this is one of the inequality constraints. So how many such equations will be there? N equations, right? So this is one condition, and there will be such n for each generator. We will have this inequality constraint, right? The total number of constraints would be n plus 1. So how do we solve this? How do we find the optimal solution? So for that, we have a mathematical tool called as Lagrangian method. So this is an optimization approach. So we will write our function as f is equal to Ct plus, that is the total cost, lambda into our equality criteria, that is PD minus sigma pi a, right? And what is it subjected to? Pi min less than or equal to Pi less than or equal to A max. Right? So this is n variables. Right. So this term should be ideally 0, right? If you are when you are done with optimization, this term will become 0, right? This part will be always 0 if your solution is correct. So that is why we have put this in our function. So the approach of finding this thing will be to take dou f. The Lagrangian approach will be taking dou f by dou pi. Right? That is, so how many such we'll have? Since we have an n generation, we have to do this for n equations, right? So you will get it as, what is Ct? Ct is C1 plus C2 plus C3 plus etc. plus Cn. So this would be the cost of ith generation divided by dou pi. Right? This is our incremental cost curve. Right? That ai plus bi, that's what we found over here, right? Plus lambda into this PD is fixed, so 0. Every other term will go away. It will be minus 1. So you found that lambda is equal to dou Ci by dou Pi, which is our incremental cost curve of I. So we see this is one interesting aspect about Lagrangian approach. So lambda for at all generators would be the same, right? Lambda would be is IC1 is equal to IC2 equal to IC3 equal to etc. to ICN. So when you're done with the optimization, this would be always same, and this is called as a, so this expression of this is called as the coordination. So basically what we're saying, to get the minimum fuel cost solution, the incremental cost of all generators must be the same, right? Shall we look at a problem to understand this better? So you are given the incremental fuel cost for 2 units. So IC1 is given as 0.1 P1 plus 20, and IC2 is given as 0.2 12 P2 plus 60, right? And both P1 and P2, right? The maximum and minimum is 125 and 20. Okay, so first let's say the first question is calculate. So if you're given PD is equal to 40 megawatt, so you're given total load is 40 megawatt right now, then you are supposed to calculate P1, P2 and lambda, right? So let's do that. So what does thing we know? P1 plus P2 is equal to 40, right? So this is equation number 1. Now then, as per coordination equation, IC1 would be, for the optimal condition, IC1 should be is equal to IC2, right? So what is IC1? It is 0.1 P1 plus 20 is equal to 0.12 P2 plus 60. So if you rearrange this, what do you get? 0.1 P1 minus 0.12 P2 is equal to minus 4. Right now, what do we have? We have two equations and two unknowns. So you should be able to solve it. So what is it? P1 plus P2 is equal to 40 and 0.1 P1 minus 0.12 P2 is equal to minus 4. So can you solve this? Let me know what the answer is. Correct. P1 is 3.63. P2 is 36.6 megawatt. So you see, based on the cost curve, this is what we found out, right? Now the question is, second question. PD. So since we know that there is a minimum generation, what is the minimum that we can generate? Well, you have to find lambda also, right? Did we find lambda? No. Can you guys calculate lambda? What is lambda? Lambda is basically IC1 is equal to IC2. Calculate both IC1 and IC2 and tell me what lambda is. Right. 0.36. But Do you guys notice a small problem? We have a small problem here. Do you guys see what the problem is? Do you guys see any problem, or is this answer correct? Is this means numerically answer is correct, but from system operation point of view, is this answer correct? You guys here? Right. So if you see, we have a condition saying that P1 should be at least 20. So the solution that we got, what is P1? It is 3.63. Yes, good. So in such cases, what we do is that we have to then hard code P1 is 20 megawatt, right? So then what will be P2? P2 would be again 40 total load minus 20, that would be 20 megawatt. This is not our ideal economic dispatch solution, but given the system condition, this would be our solution, right? So if we calculate delta IC1 and IC2, you will get this as 22, and I think you will get this as 18.4. So in this case, this one did not participate in economic load dispatch. This one just was fixed. So for whichever generator we calculated P2, then we have to do that. Would be our lambda. So suppose we have three generators. Suppose P1, P2, P3, right? In this case, what we'll do is that, say suppose if one generator is sitting low, then we will fix this at the maximum, and then we will do economic load dispatch again with the other two generators. Is that clear? Okay. Say suppose, let's try it this way. Okay, do this. Then you probably will understand. Say P1 is equal to 0.1. So C1 is equal to C1 is equal to 0.1 P1 plus IC2 is equal to 0.1 P1 plus 5. IC3 is equal to 0.2 P3 plus 6, right? And the limits are P1 less than or equal to P2 is less than or equal to and P3 less than or equal to 10 less than or equal to 100. So if PD is say 120 megawatt. Calculate P1, P2, P3. Can you calculate P1, P2, P3 for this one? Let's do this. P1 plus P2 plus P3 is equal to, we can say LC1 is equal to LC2 and LC1 is equal to LC3. And to do that, you will get 1 P1 minus 1 P2 is equal to minus 1 P2 equal to minus 1. Right? So if you add equation 1 and 2, you multiply this equation by 10, so you will get P1 minus P2 is equal to minus 50. So if you add this equation and this equation, you will get P3 as 70 megawatts. Are you guys trying? Do this and this, and I will get bracket over here. 121. What is that? What's 20? 3 is equal to 30. Okay. P1 plus P3 is equal to 7. And if you arrange this, you will get 1 P1 minus 0.2 P3 is equal to minus 4. P1 is equal to 20. Okay. So what is P2? You just subtract it. P1 plus P2 is 50. So 120 70. P3 is P2 is 70. Right? Multiply by 10 is okay. P1 basically we got P1 plus P3 is 70. That's the equation. No, there's something wrong over here. Yeah, 70, correct. So as per his solution, you get, so this is one equation, and if you rearrange this IC1 is equal to IC3, you will get 0.1 P1 plus 10 is equal to 0.2 P3 plus 6. So if you rearrange this, you will get 0.1 P1 minus 0.2 P3 is equal to minus 4, right? So we can eliminate either. So let's multiply the 0.5, so that will be 0.5 P1 minus P3 is equal to minus 2. So now if you add these two equations, you will get 2.5 P1 is equal to 2.5 is 5. So 25 P1 is equal to 50. So you will get 7 P1 is equal to, how did you get? Right, sorry. So you know P1 plus P2 plus P3. Did you guys solve? Tadro, did you also get the same answer? P1 plus P2 plus P3. P2 is 70. Oh, that's correct. P2 is 70. Correct. P1 plus P2 is 70. Sorry, is 120. My bad. Right. Then if you redo this, 0.1 P1 minus 0.2 P2 equal to 0.1 P1 minus 0.2 P2 is equal to 5 minus 10 minus 5. Right? So multiply both sides by 0.1, you will get P1 minus P2 is equal to minus 50. So if I add these two equations, what will I get? 2P1 plus P3 is equal to 70. So this is our equation number 1. Now if I can equate these two, alright, what will I get? 0.1 P1 plus 10 is equal to 0.2 P3 plus 6. So if I rearrange this, what will I get? 0.1 P1 minus 0.2 P3 is equal to minus 4. So let's multiply both sides by 5. So I'll get 0.5 P1, right, minus P3 is equal to minus 20. Right. Now if I add these two equations, what will I get? 2.5 P1 is equal to 50. So what is P1? 50 divided by 2.5. So you will get it as 20. So what is P3? P3 would be 50. And if you substitute this back, you get as P2 as 70. Right? Correct. Is that clear? Correct. So what is P1? P1 is 20. P2 is 70, P3 is 30, right? So let me do something here. Let me put the lower limit as 30 instead, right? So now we have come to the problem that P2, P1 has to be 30, right? So then we need, so what we will do is we will fix P1 as 30 and we will do economic load dispatch with the other two. So now what is the condition? P1 is 30. So P2 plus P3 has to supply how much? 120 minus 30. So that will be 90. And what is the condition? IC2 will be equal to IC3, right? So you will get this as 0.1 P2 plus 5 is equal to 0.2 P3 plus 6, right? So if you rearrange this, you will get it as 0.1 P2 minus 0.2 P3 is equal to 1. So I can multiply both sides by 5. So you will get this 0.5 P2 minus P3 is equal to 5. So if you add both, you will get 2.5 P2 is equal to 95. So you will get P2 as 95 divided by 2.5. This is 38 and P3 would be 52. So you see, when the limit changes, if the generator, if more generators are there, then we'll fix the generator limit and we will do the economic load dispatch based on that. And in this case, what would be lambda? Lambda would be, you substitute this in either of this equation, you will get the same. So that would be 3.8 plus 5. That is 8.8. Is this clear? Okay. So let's do a few more questions. So the cost of a generating unit is given as this much. If it is rated, 15 megawatt, 11 kV, right? What is the incremental cost when delivering maximum power? So you are given the cost curve equation, right? You are given the system generator rating. They are asking you to find the incremental cost when delivering maximum power. Are you guys trying this? Okay, got it as 2. Mm, no, that's not. It's not. How did you get that? So what are they asking? They are asking for incremental cost at maximum power. What is incremental cost? It is the you take the derivative of this. So it will be 0.04 pi plus 53. And what is the maximum power that can be generated? It will be 50. So if you substitute that, you will get it as 0.04 into 50 plus 53. It will come as. So is that clear? Right. Yeah. The value that you calculated possibly is, but how did you get 254? So 53 into 50 plus 225 plus 50 square into 0.02. So what is the maximum total cost? T max. Substitute 50 over here and I think you will get it as 2925. Is this clear? Right. Let's do a few more questions, I guess. F1 is equal to 0.2 T1 square plus 30 T1 plus 60. And F2 is given as 0.15 P2 square plus 20 P2 plus 80. Both rupees per hour. right? So given, so somebody did economic load dispatch and they found lambda is 120 rupees per megawatt hour. So they are asking what is the load. So you are given the cost curve and you are given that lambda is 120 rupees per hour. They are asking you to find what is the load. Can you guys give this an attempt? Okay. You guys are still able to hear me, right? Okay, good. Because I lost power at my house. Good. Are you guys, do you know how to attempt this question? Okay, good. Okay, what it is? 558.3. Yes, correct. Varun, did you get that same answer or do you need help? Correct. 58.3 is the correct answer. Okay, good. Right. So let's do one more question and then we'll proceed to the concept with losses. Okay, so you are given f1 is equal to 1.5 p1 square plus p1 plus 30, and f2 is equal to 0.2 p2 square plus 16 p2 plus 20, right? Right. You guys are able to hear me, right? Okay, good. So you are given the fuel cost for two generators, and this is how the load varies for 24 hours. They are asking you to calculate total fuel cost for the day, and they are not keeping any generator limits. They are just asking you to calculate the total fuel cost of the day. Can you do this? Do you have an idea how to do this? Okay, good. So I'll give you 5 minutes to do this, right? 10:55. F2 is 0.2 P2 square plus 16 P2 plus 20. Did you guys get the answer? Okay. So we have two load conditions, right? So what is the first condition? First is PL is equal to 100, and we have second condition PL is equal to 200, right? Right. So in the first case, if you take dou F1 by dou P1, In both cases, let's find the incremental first cost. So it's just dou x1 by dou p1. What do you get? 0.3 p1 plus 20, and what we get is dou f2 by p2. So your incremental cost will get it as 16. So let's take the case one where load is 100 megawatt. So this is from 0 to 6 and 18 to 24, right? Right. So we have in this case P1 plus P2 is equal to 100, and if you do this, you will get this as 0.3 P1 plus minus 0.4 P2 is equal to minus 4, right? So if you solve these two equations, you will get P1 is equal to 51.42 and P2 is equal to 48.57, right? Similarly, the second condition is when total load is 200 megawatt, right? So in that case, it becomes P1 plus P2 is equal to 200, and again same equation 0.3 P1 minus 0.4 P2 is equal to minus 4. Right? So if you solve this, you will get P1 is equal to 108.57 and P2 is equal to 91.43, right? So basically, so this is between 0 and 6 and 18 and 24. This is between 6 and 18, right? So for 12 hours, generator 1 is generating 51, and for 12 hours, this is generating 40.57. For 12 hours, it's 100, and 12 hours, this is this thing. So what will be the total cost? You substitute that in the equation. So we know F1 is equal to 0.15 P1 square plus 20 P1 plus 30, right? This rupees per megawatt, right? And what is it to 0.2 P2 square plus 16 P2 plus 20, right? So for the 100 megawatt condition, when the total load is 100 megawatt, what is F1? F1 will be 0.12 plus 1 plus 20 into this thing plus 30. So this would come as 1455 rupees per hour, right? So, and what would be F2? Always calculating. One two 68.9 rupees per. So when you do the same thing for 200, you can calculate F1 and F2. So you will get this as 2947 rupees per hour. And this is 3157, right? Rupees per hour. So what you need to do, this, let's call this as FA, FB, FC, and FP, right? So basically it is FA plus FB into, so this is operational for 12 hours, right? And FC plus FP is also for 12 hours. And you take the sum, right? So the final cost, I think you will get it as 118,176, right? Is that clear? Okay. So we will just look at one more topic. Okay, just going out of time because means going a little more ahead because I think we have one more session to finish this. So let's look at with loss also. Is that okay with you guys? Maybe 15 minutes extra. Is that okay? So if you go for another 15 minutes, is that okay with you guys? Let's just quickly look at the condition with losses also. Right? It's also important. Right. So with losses, what happens? The condition that we need to meet is PD, P demand plus P loss is equal to sigma Pi. So if you remember our Lagrangian function, it is minimize F. So here in this case we have to say minimize total cost with what is the condition? PD plus PL minus sigma Pi, right? Subject to the conditions is still say that Pi is less than or equal to max and min. Okay? So that condition still holds, right? So how do we do the Lagrangian approach? We differentiate this function with respect to right. So this would be dou Ci by dou Pi. Earlier it was just plus lambda, right? The other term went to 0. 1 here. Since here we will have dou PL by dou PI minus 1. So this is our incremental transmission loss. So when PI increases, how do the total system loss increases? So if you see, so this is going to be the factor. Earlier we were saying that this is going to be this should be the same for all generators, right? So this is our lambda. So what is lambda? Okay. So what is our lambda over here? In this case, lambda would be, if you rearrange this, this is our incremental cost ICI, right? Yes. 100 into 1 minus duplicate. So we tend to call this as this factor is called as penalty factor. So due to the system losses, our incremental cost is affected. It's affected, goes up a bit, right? And this is called as penalty factor. And lambda would be Li ICI, right? Incremental cost into Li. Where Li is the penalty factor. So the coordination equation becomes lambda is equal to L1 IC1 is equal to L2 IC2 is equal to etc. is equal to Ln ICN. Earlier, we were not considering loss. It was lambda is equal to IC1 equal to IC2 equal to ICN. Here, losses are considered. Penalty factor also comes into picture. So this is our new coordination equation with respect to losses. Right. So penalty factor increases and decreases with respect to a lot of factors, right? So let's look at how the losses are, how all the losses come into picture. So that for a two-line system, right, P loss is given as B11. Okay, let's rewrite this actually. So suppose we have this kind of a system. So that is our load. This is our G1. This is our G2. Okay. right? So suppose I1 is flowing from here and I2 is flowing from here, right? So this is the I3 is I1 plus I2, right? So what is the total? So suppose the resistance of this line is R1, this line is R2, and this line is R3, right? So what is power loss? 3 I1 square R1 plus P I2 square R2 plus 3 I1 plus I2 the whole square R3, right? And what is I1? I1 is V1 divided by root 3 V1 power factor 1, right? And what is I2? V2, or we can just let's assume let's forget about this one. Let's put it as root 3 V2. Let's assume power factor 1. Power factor is 1, there will be losses, right? Power factor 2, right? Should be S divided by P divided by, correct? Power factor 2, right? So if you substitute this and rearrange, you can get this in terms of, so you will get P loss as R1 plus R3. If you rearrange this, you will get this as R1 plus R3 divided by V1 cos phi 1 whole square V1 square plus R2 plus R3 divided by V2 cos phi 2 the whole square plus 2R3 divided by V1 V2 cos phi 1 cos phi 2 V1 V2, right? So if we generalize this, we will get P loss is equal to B11 P1 square plus B22 P2 square plus B12 P1 P2. Clear? So for n generation, it would be a combination of this. So for two generators, so for this is for two generators. So for n generators, P loss would be sigma I is equal to 1 to n sigma j is equal to 1 to n. So it will be a combination EI PJ BIJ. Right? Let's write it in the next slide. So P loss is equal to sigma I is equal to 1 to n sigma j is equal to 1 to n Bij Pi. Clear? Yeah, so is this clear? Let's do two questions, right? That will help you understand better. Are you guys with me so far? So let's do a question. So you are given the incremental cost curve. Then P loss is given as okay, if the lambda is equal to 117.6 rupees per megawatt hour. Calculate P1, P2, P load and P losses. Can you give it a try? Do you want? Okay, I'll solve this one with you, so that the next one you can try on your own. Okay. So we are given IC1, IC2, and all those things, right? So what do we know? Lambda is equal to Li ICI, right? So let's calculate L1. What is L1? L1 would be 1 divided by 1 minus dou Fi by dou P, or dou losses by dou PI. Since if you see the loss equation, it is not related to Pg2, so this would be 0. So L1 would be 1, right? So lambda is equal to IC1. So what would be IC1? It would be That is 0.35 Pg1 plus 41, right? So 0.35 Pg1 or P1 plus 41 is equal to 117.6. So if you solve this, what do you get? P1 as you get it as 218.8. 218.8. What is L2? Should be 1 divided by 1 minus dou L by dou P2. But dou L by dou P2 we are given, right? So what is dou L by dou P2? Hang on. So if you express, this would be 0.001 into Pg2 square minus 140 Pg2 plus 70 square, right? So if you take dou L by dou Pg2, it will be 2 Pg minus 140 into 0.001 into 10 power minus 3, right? So this would be basically 0.002 into Pg2 minus 70, right? So plus 12 by 2 minus, right? So now what does this mean? 0.35 P2 plus 41 divided by 1 minus 0.002 into P2 minus 70 is equal to 117.6. So you can bring it over here and rearrange and solve. You will Pg2 as how much? 159.03. Right. Now there is the tricky part. So the total generation is 218.8 plus 159.03. Now how much is the losses and how much is the load? So we know the expression for P loss, right? What is P loss? It is Pg minus 70, sorry, P2 minus 70, the whole square into 0.001. So if you do that, you will get it as 7.92 megawatt. Why is this pen not working today? And PD will be P1 plus P2 minus PL. So if you do that, you will get it as you will get it as 369.9. Is this clear? Okay. So what we'll do right now is we will stop here, and in the next class we will look at frequency control and little aspects of power protection, and whatever doubts you have. Probably the last next class will be mostly likely our last class. So we have some portions left of load frequency control and some portions about protection. And if whatever doubts you have or whatever questions you have, you can bring it in the next class and we will discuss it. Right? I think we have a class on Sunday, so bring it then. Right? As I say, keep trying questions. Sign up for as many tests as possible. Right? Kuro, you were saying something? So this topic is kind of important, right? For quick economic discuss, because this is something. Not saying that the question might come, but given that they have reintroduced this as a new topic in our syllabus, this was not there in our syllabus, even though we used to teach. But this they have very specifically added in the syllabus this year. So it would be wise to look at this topic and the questions from this, right? So they might ask you a combination of penalty factor, lambda, and incremental cost. So that is kind of tricky and confusing for people. So try to understand the concept clearly. Okay. Right. So I'm going to stop over here. See you in the next class. Thank you.